So we have Mikhail, who's going to talk about forward and backwards compatibility for security features.
Hello everyone. My name is Mikhail Salin. So I work for Microsoft, and I'm mostly the maintainer of LANLAC, which is a new security Linux feature. It's about sandboxing. So this talk is about ROS library we wrote for LANLAC, and we kind of had some challenges about compatibility. So just a quick introduction, context to understand the problematic here. Why care about security? So here, it might be obvious for some, but like every application can be compromised. Every application can be trusted at first, and during the lifetime of a process, it can become malicious. As developer, there's multiple problems. So we don't want to participate to malicious actions performed by attackers through our software, and we kind of have a responsibility for users, especially to protect their personal data. And there's also there might be some issues about third-party code. So security sandboxing is a security approach to isolate software, and mainly to isolate them by dropping ambient access rights. So in a nutshell, when you launch an application in common Linux distro, this application can access a lot of files, including some which are kind of private, like .ssh, for example. So sandboxing should not be confused with namespaces and containers, which is a way to create kind of a virtualized environments. And SecComp is also something which is really interesting for security purposes, but it's not about access control. It's about protecting the kernel. That was initially the initial goal of SecComp. So LANLAC is really dedicated from the ground to bring sandboxing features to Linux. So to bring some security features to the kernel. So it is an access control system available to every processes. You don't need to be root or whatever. And it is designed to be embedded in applications. So to create built-in sandboxing. It's a way to create one or even multiple layers of new securities. So it comes kind of after all system-wide access control which are already in place. And so it's available on most distros nowadays. And if it is not the case, I encourage you to open an issue in your favorite distro. So about sandboxing here, what the interesting point about sandboxing and built-in application security is that we can create tailored security policies and embed them in the application. So there is interesting things about that, and that might help to make it security invisible, which is kind of the main purpose here. We want to not bother users, but secure them anyway. So because this security policy can be embedded in the application, it can use the application semantic. You can also use the application configuration transparently, so you don't need to add another configuration stuff. It's not another layer of execution. It's embedded in the application. And of course, if the configuration depends on user interaction, it can adapt to this change of behavior. And one really interesting point is, as developer, you want to test what you do, and you want to kind of get guarantees that whatever you're developing is still working. And being able to embed security policies in your application make it possible to test them the same way that you can test every other features. So that's really interesting. You don't rely on, let's say, Linux being installed on your test machine and so on. And it adapts to the application over time. So if you have a CI which is well configured, you can test it and make sure that well, you can add new features, update the security policy, and make sure that everything was as expected. So speaking about the library and the Rust library, so the idea was to create obviously something which is Rusty, so idiomatic to Rust. And for this, well, we wanted to leverage strong typing, so to get some developing guarantees, and also to follow some common patterns. So mainly here, the builder pattern. So it's still a work in progress. It's working, but yeah, we're working on improving the API and make it easier and more easy to use for compatibility reasons. So this talk about this kind of compatibility requirements, and yeah, so I'll talk about that. Some example of early public users are listed here, but yeah, it's still in kind of beta for now. So let's start with some code example. So just as a warning, this kind of a simplified code, it's working. But yeah, for the demo, well, it's not demo, but for this example, the idea is to make it simple to make it easier to understand. So you can see at the left, there's a C code, and at the right, the exact same semantic, but in Rust. So I will mostly talk about the Rust code, but yeah, you can take a look at the C code to kind of see the difference between them and how Rust can be useful there. So as I said, it is based on the builder pattern. So you create a rule set object here with the rule set new, and from there you kind of call different methods to well, build the object here. In this case, a rule set. So a rule set will contain a set of rules, and yeah, at first you define what you want to enforce, what you want to restrict, what you want to deny by default. So in this case, it is two actions: the action to execute files and the action to write on files. So obviously it's not enough, but in this case it's easy to understand for this simple use case. And then once you define the rule set and what the rule set can handle, well, you can create it. And the rule set creation translates to, you can see at the left, there's a long create rule set, and this function is in fact a syscall. So in the Rust part, when you call the create method, it creates a new rule set, which is backed underneath by a new file descriptor dedicated to Larnock. And that is wrapped in the rule set object. Then, if you want to add rules to allow some directory to be, for example, executable, which is the case here, so well, you open the /user directory, and you make it well, executable. So allow access first, execute. And then you can add all the rule you want for all the execution that should be legitimate for the, well, a legitimate use case. And then you restrict the current process. Well, in fact, the current thread. And from this point, the current thread can only execute files which are in /user. And it cannot write anything at all, actually. So that was an introduction, quick introduction to the library. And the thing is, Larnock is not a full feature access control yet, because, well, it is complex. And, well, to reach this goal, well, we need to spend much more years to increment, well, to add new feature to Linux kernel. Yeah, and the thing is, well, sometimes you might add new features that enable to restrict more, and sometimes we might add some features to restrict less. So let's see what this means. So the first version of Larnock, which was released with the 5.13 kernel, basically allowed to read, write, and do a lot of common stuff to restrict a lot of common file system actions. But there was, like you can see here, there's three categories. The first one, always denied, was for the first version of Larnock, the action that was always denied whenever you sandboxed a thread. So that was for, well, complexity in the development, but also security reasons. So, for example, you are not able to execute set2id binaries because it will be kind of a way to bypass the sandbox. And there's also some restriction on ptrace, so you're not allowed to debug an application process which is outside the sandbox. Obviously, it will be a way to get out of the sandbox. So that's not what we want. So the second version of Lanlock had its new way, a new access right, which is a way to reparent files. So at first, it was denied to change the parent directory of a file for security reasons, because Lanlock is based on file hierarchies identification, and that was kind of complex. So, but with the second version, we implemented that, and then it became configurable. So one item less in the always deny box. In the third version of Lanlock, so all these versions are new kernel releases. And in the third version, we added a new way to restrict file truncation. So truncation in a nutshell is to change the size of a file. And this was always allowed before because it wasn't handled. It was a bit complex to implement this in the kernel at the time, but now it is possible. So you can see that we can move items from the always deny box to the configurable, and from the always allowed box to the configurable list. So application compatibility. There's two main things in compatibility. There's forward compatibility in a way that when you update your kernel, you still can use the old kernel features. So that's kind of common. And the backward compatibility in this case is, well, when you're using a kernel feature, well, you might need a specific version of the kernel that supports this feature. And if your application is running, is launched on an old kernel, well, that feature might be missing. And the thing is, when you're developing an application, well, you don't know on which kernel your application will run because, well, it's a user choice and a distro choice. What comes with Lanlock is the ability to get the Lanlock, what we call the ABI version. So it's really just a number that increments that started at 1 and then increment for each new set of features which is added to the kernel. So to give you an idea, it's really simple to get this ID, this version. It's with a Lanlock create rule set syscall with a specific flag. So yeah, it's a C code, but it's really simple. So what we want to do at first, well, there's four main properties. The first one is to be able to, well, to make it easy to use for developers, of course. So we want something which is generic, which kind of follows the builder pattern because, well, it's kind of common and easy to use. We want developer to focus on what they want to restrict, not the internal, well, implementation in the kernel. And we want them to gradually go from a coarse-grained access restriction to a fine-grained one. So we don't want them to need to implement a fine-grained at first. It might be difficult. So yeah, in the same way that we can incrementally add new set of features, we can also incrementally restrict more and more over time. So no need to be super strict at first. And yeah, it should be simpler to write, well, for the common cases. OK, at first, a first improvement was to create group access rights. So let's say you know which Lanlock version is supported by the running kernel. Let's say it's the second version. Then you can create a new root set, which will get all the access rights which are supported by this specific kernel. So you just call the handle access with accessfs from all and then ABI2. And then you can do kind of the same when you're adding a new rule. And this time, well, you want to add an exception on the /user to make it readable. So in this case, there's two main groups, the from read and the from write. So for example, the from read includes reading a file, but also reading a directory. so listing a directory. Okay, second property that we like to have is being able to enforce a strict restriction. So even if we don't know on which kernel the application will run, on some cases we might want to be sure that all features are enforced and restricted. There's two use cases here. The first one is to test it. If you want to sandbox an applications, you want to make sure that even if you're using all the sandboxing features, well, your application will work as expected. So that's really important. And you don't want to run your application in an old kernel and kind of be fooled by the fact that your application is running because there's no, well, not all security features are enabled. So you want to catch these kind of issues in your CI. And also for security software, you want to have some security guarantees. So you want to have a way to follow the whole sandboxing with all security features that we embedded in our application. The third property is to be able to enforce the best default security with some minimal requirements. So that's kind of the opposite. And this use case is mainly for end users because end user, well, you don't know which kernel they will use. And so you want to be able to enforce an opportunistic sandboxing. So if they have a new kernel, well, they will be more protected. If they have an old kernel, they might not be protected at all, but that's not your choice. That's their choice. And at the end, they want to run your application anyway. So another requirement is to be able to disable the whole sandboxing if some features which are required may not be met. And this approach should be easier to write than others because it is the most common things to do. And the last property is being able to run, well, to configure at runtime the sandboxing, but to make it in a way that you're running most of the code. So the idea is to be able to have kind of the same code running everywhere, almost, even if they don't have a recent kernel. Why that? Because you want to kind of identify early kind of some issues which might be linked to the sandboxing code. And that if you have, let's say, 2 users using a recent kernel and 4 users using an old kernel, well, you might want to test as much as possible with all your users, even if they don't have a newer kernel. So the first approach we took was, so I'll go quickly here. There's 3 approaches. The first one was to change, to add a new method to the rule set builder pattern. So it was a simple method to set or unset the best default approach. So if it was false, it was required to have this feature. So in the example, an application that need to move files from one directory to another needed to have the accessfs refer access right to allow this access. And if it wasn't the case, well, the sandboxing should not be enforced, otherwise it will break the application. So that is a requirement. And in this case, so that was a way to kind of change the state of the builder over time. So this is kind of flexible, easy to understand, but there's some kernel cases. And yeah, it makes the code not really clean. Another approach was kind of to do the same, but this time with, instead of 2 shifts, enable or disable, there were 3 ways to change it. The best default way, the soft requirement, and the hard requirement. So a way to make it best default, a way to make it error out if there is any unsupported feature, and a way to disable the sandbox without error if some features were not supported. So that wasn't ideal in either. And the last approach, which is currently a work in progress, is kind of a new one. So the idea is to make it still configurable and to follow all these properties, but to make it a bit simpler and still flexible. So here, in a nutshell, well, you can make a new rule set that will error out if there's any unsupported features, but at the same time, you can specify which feature is required to enable the sandbox or not. So that's kind of specific, but yeah, should be better. So going forward, there's a lot going on in this Rust library, a lot to improve. New helpers, new documentation, and I encourage you to well, sandbox your application or others. And well, there's some tips if you want to get some motivation here. There's some rewards program. So thank you for your attention. There's some interesting link here. This talk was kind of dense, but I hope you enjoyed it. Thank you.